Uniformly accelerated motion. Accelerated motion can be positive, speeding up, or negative, slowing down. Acceleration means we're speeding up, positive, AAV. Deceleration means that we're slowing down. If we use the word deceleration or decelerate, do not include the negative in your answer. So, if you're going to use the negative, you still make reference to the word, and you still use the terminology acceleration, but with the negative. We're accelerating at negative 10 kilometers per hour per second. If you're going to use the word decelerate, remove the negative, because the word decelerate tells us that we're looking at it in terms of slowing down. Yeah?
Which one's more correct?
Either. Either one is correct. Either one. Okay, I will accept any one of the terms. Just remember, though, if you're going to use the word decelerate in your calculations, make sure you substitute into the equation a negative number for the answer. So acceleration can also be found from a speed time graph. We looked at distance time graphs when we were talking about average speed. Now, with regards to average acceleration, we are graphing average acceleration using what we call a speed time graph. So, comparing uniform motion and uniformly accelerated motion. So here we have uniformly accelerated motion. Uniform motion shows a straight horizontal line on a speed time graph. So notice at every single second of time, the speed is exactly the same. So we have a straight horizontal line. So what is the object telling us? Are we increasing our speed? No. So are we accelerating? No, we are not accelerating. We are going at a constant speed. Are we accelerating? No. So in fact, this is not uniformly accelerated motion. Pretty much the speed at every single second of time is exactly the same. So we are not really increasing our speed. So this is what we call uniform motion, not uniformly accelerated motion. Because we're not accelerating, we're not speeding up. The time or the speed that we are going at every single second is exactly the same. Now, any change in an object's speed or direction means that its motion is not uniform. One type of accelerated motion is called uniformly accelerated motion. And here we have this motion of an object that travels in a straight line and has its speed changing steadily with time. The following graph gives an example of uniformly accelerated motion for an object that starts from rest and increases its speed by 5 meters per second every second. So here we have our table, and we're going to graph the table. And every single second in time, the speed is increasing by 5 meters per second. So we have accelerated motion, but in a uniform fashion. So it's the same. So we're all dressed, but we're all in full uniform here in class. So we're all the same. With regards to accelerated motion, uniformly accelerated motion, it means that the acceleration is the same at every interval of time. Uniformly accelerated motion also occurs when an object traveling in a straight line is slowing down steadily. The following graph shows an object undergoing decelerated motion or a negative accelerated motion. So notice the two types of terminology I use to refer to something slowing down. Either negatively accelerated or decelerated motion. So it shows uniformly negative accelerated motion of an object slowing down steadily from 20 meters per second to 0 meters per second in 4 seconds. So we are slowing down by about 5 meters per second every single second in time. we're coming to a complete stop. So our V1 and our V2 is down here. So we're going to get a negative delta V, negative delta V divided by a positive delta T. Remember, time can never be negative because we cannot go back in time. The speed technically cannot be negative. Only acceleration can be negative. So here we have non-uniformly accelerated motion. If an object is changing its speed in an unsteady fashion, its motion is non-uniform. So non-uniform, different intervals. So each interval is not consistent. So maybe for the first little bit, it might accelerate 10 meters per second. And the next one, it might accelerate maybe 7 meters per second. The next second in time, it might accelerate only 2 meters per second until it reaches its final speed. So notice here, at each second interval here, we have the speed goes from 0 to 10 meters per second in the first second. And then it goes maybe here to about 16 meters per second. Then to about 19 meters per second. And then finally 20 meters per second. So the speed is increasing really quickly at the start, and then it's slowing, it's not increasing its speed as quickly because pretty much the slope here of the object is not as steep. So here are our calculations that we used. Now, speed time graphs for acceleration. The type of slope of a speed time graph tells us a lot about the type of acceleration. A positive slope represents a positive acceleration, so the object is speeding up. A negative slope represents a negative acceleration. Object is slowing down, going in the opposite direction. So the blue line represents positive slope, right, going in a positive direction, which means the object is speeding up. The red line is showing in a negative slope, slowing down. So therefore, the slope of a line on a speed time graph gives us the acceleration. We looked at distance time graphs, and a distance time graph allowed us to calculate the slope, which would give us the average speed. But on a speed time graph, the speed time graph allows us to use the slope to help us calculate the acceleration. So let's recall the slope equation. Slope is equal to rise over run, which in math translated to our delta y over delta x. But our delta y represents our speed. Our delta x represents our time. And the delta v translates to v2 subtracted by v1 over t2 subtracted by t1. And most of the times, what's t1? 0. To help us calculate our AAV. So, in other words, instead of slope, really, by doing all this, we're trying to find AAV. So if we take our line, we find any 2 points, we calculate our rise and run. So our rise we have, according to this little graph, 25 minus 5. So it translates to a delta V of 20 meters per second divided by 4 meters per second, which would give us an average acceleration of 5 meters per second, or 5 meters per second squared. Either or I will accept. They are both exactly correct. So, area under the line on a speed time graph. So, since V is equal to delta D over delta T, then delta D is equal to V times delta T. Objects here we have, what kind of object do we have underneath the line? Triangle. So the area of a triangle is base times height divided by 2. So, but according to this, it says to calculate our delta D, we use V times delta T. Right? So base times the height. It ignores the divided by 2. So, if we look at the following, the distance traveled can be calculated by multiplying the speed with the time. That's what we said. Right? delta D is equal to V times delta T. But the distance traveled for the same object is really 250 meters, because on a speed time graph, the distance is found by calculating the area underneath the graph. So if we find our base, so our base is 10 seconds, our height is 50 meters per second. So base times height divided by 2 will give me the distance traveled. So it doesn't work with graphs as it would in a regular word problem. It works only on the speed versus time graph. So to calculate the average, the distance traveled only on a speed time graph is to calculate the area underneath the line.